Hello everyone. Today we are going to see about properties of integral. If f1 belongs to R of alpha, that means Riemann-Stieltjes integral, and f2 belongs to R of alpha, that also belongs to the Riemann-Stieltjes integral on a comma b, then f1 plus f2 belongs to R of alpha, and f belongs to R of alpha for every constant. C is a constant, and in integral a to b f1 f2 d alpha equal to integral a to b f1 d alpha plus integral a to b f2 d alpha, and also for integral c f d alpha equal to c into a to b f d alpha. This one we have to prove. So for that proof, let us consider f equal to f1 plus f2. So and p be the partition of a comma b. So p be the partition. P is the single partition with the function f1 and f2. So how we write means, if lower bound of p f1 comma alpha plus lower bound of p f2 comma alpha less than or equal to, here the partition is nothing but p, so single partition with functions, that is the addition of two functions. So addition means we have to split lp f1 comma alpha plus lp f2 comma alpha, that is less than or equal to the whole function l of p f comma alpha less than or equal to up comma f comma alpha less than or equal to, how we split means f1 plus f2. So u of p f1 comma alpha plus u of p f2 comma alpha. This is the first equation we consider. We from the question we know that f1 belongs to R of alpha. So f1 belongs to R of alpha means the universal form of definition is epsilon greater than 0 be given, there exists a partition. Here we exist a partition of p1, because the function are splitted into two terms, so we have to split the partition into two terms. So p1 means, how we write means, the general form is upf comma alpha minus lpf comma alpha. So for here function also f1 and partition is p1, so we have to write u p1 f1 comma alpha minus l p1 f1 comma alpha less than, why we write epsilon by 2 means we have to split the, we had split the partition p as p1 and p2. So for that we write epsilon by 2. And for next form, f2 belongs to R of alpha means that exists a partition p2. So how we write u p2 f2 comma alpha minus l p2 f2 comma alpha less than epsilon by 2. We take the common refinement. Common refinement is both the both the forms are written in one form. So p equal to p1 union p2 be the common refinement means, how we write means, the p1 and p2 can be written as p. So the above form can be written as u p f1 comma alpha minus l p f1 comma alpha less than epsilon by 2, and this form we take a p1 and p2 as a common refinement, so instead of p2 we can write p. So u p f2 comma alpha minus l p f2 comma alpha less than epsilon by 2. From 1 what we know means upper bound minus lower bound, u p f comma alpha minus lpf comma alpha, that can be written in the form of, how we write upf comma alpha means, this can be written as the function is f1 and f2. So up f1 comma alpha plus up f2 comma alpha, and l can be written as here having a minus, so minus l p1 p f comma f1 comma alpha minus l p f2 comma alpha. So we from the above we know that up f1 comma alpha minus lp f1 comma alpha less than epsilon by 2. So this term is epsilon by 2 and this term also epsilon by 2. Epsilon by 2 plus epsilon by 2 is epsilon. So for that here f belongs to R of alpha. What we consider for f equal to f1 plus f2. So f1 plus f2 also belongs to R of alpha. We proved. Then what we do means, we have to prove the integral term. We proved that f1 f2 belongs to R of alpha. Then we have to prove the integral term. So integral term means integral a to b f1 plus f2 d alpha equal to integral a to b f1 d alpha plus integral a to b f2 d alpha. So for some partition p we have means, what we are doing means, consider this form, general form, that is upf comma alpha minus l p f comma alpha that is less than epsilon. Here we consider two partitions, so only we put epsilon by 2. Then what we do means, instead of u p f comma alpha, we take minus l on that side, means what we get means less than epsilon plus L of P f comma alpha. So in L of P, how we write means the lower bound form u p f comma alpha less than or equal to epsilon plus integral a to b f d alpha. We can write this form. So upper bound p of fi comma alpha less than or equal to a to b fi d alpha plus epsilon by 2. Here I equal to, we consider only two partitions, so 1 and 2, since f1 and f2 also belongs to R alpha from 1. So now what we do means, integral a to b f d alpha less than or equal to u p f comma alpha. How we write means, here epsilon becomes arbitrary, means we can write this form. So less than or equal to, p can be splitted into u p1 u p f1 comma alpha plus u p f2 comma alpha. So we can write this form as integral a to b f1 d alpha plus epsilon by 2. By we are assuming that fi alpha equal to, we can write this form. Instead of I, we can replace f1. Instead of I, we can replace 1 and 2. So if we replace 1 and 2 means, we get this term in the f1 d alpha plus epsilon by 2 and f2 d alpha plus epsilon by 2. So only we write here. Then f1 plus d alpha plus a to b f2 d alpha plus epsilon by 2 plus epsilon by 2 is epsilon. So here epsilon is arbitrary, means that epsilon equal to 0. Then what we get means, integral a to b f d alpha equal less than or equal to a to b f1 d alpha plus a to b f2 d alpha. This also we proved. What we do for next means, we have to replace f1 and f2 by minus f1 and minus f2 for this here having a less than or equal to. So we have to replace minus f and convert this as a greater than or equal to. From this term and this, the greater than and less than assuming means, we can replace as equal to. So epsilon is arbitrary, means we get this point. Replace f1 as minus f, replace all the f terms by minus values. So integral a to b, we can replace the symbol also less than or equal to as greater than or equal to, because we are multiplying with minus. So minus a to b f d alpha greater than or equal to minus a to b f1 d alpha plus a to b f2 d alpha, and both the side minus are getting cancelled. From this term and this term, we can see the symbols only changes. So this one is less than or equal to, this one is greater than or equal to. From 5 and 6 we conclude that both the terms are equal. So a to b f d alpha equal to a to b f1 d alpha plus a to b f2 d alpha. This is the form. Then for third question, we have to prove that a to b c f d alpha equal to c into a to b f d alpha. So for that, first we have to prove that first we have to prove that cf belongs to R alpha. Then we have to prove the integral form. So for that, for this case, CF belongs to R of alpha, then A to B CF d alpha equal to C into A to B F d alpha. First case, consider C equal to 0. Then second case, what we do means, if C equal to 0 means all the terms are gone out. So if case 2 C not equal to 0 means F belongs to R alpha, means we know that the condition minus A to B F d alpha equal to A to minus B F d alpha equal to A to B F d alpha. And for a universal form of this, let epsilon greater than 0 be given, there exists a partition, then upper bound minus lower bound less than epsilon by 2. For here we split the to prove. What we have to prove means CF also a function. So UP CF comma alpha minus LP CF comma alpha less than epsilon. We know that small mi and capital Mi are the infimum and supremum of xi minus 1 and xi. Likewise also c into capital Mi, c into small mi also infimum and supremum of the xi minus 1 and xi. So here consider the upper bound upf comma alpha. We are considering here cf. So upcf comma alpha equal to, we can generally write this term as in the summation form. Summation I equal to 1 to n c mi delta alpha I. Taken out c on this side means we get I equal to 1 to n mi delta alpha I. C equal to, this can be written in the form of upper, we are writing this term as a summation of this value. We can able to write u, we can able to write here not having c means what we have in the term u p f comma alpha. Okay, then we have also put lower bound p comma cf comma alpha equal to summation I equal to 1 to n ci delta alpha I. Taken out c means we get this term. This term can be written as l of p f comma alpha. So for from 2 and 3 we know we can conclude this one, and we can conclude this one and subtract, and if we subtract this means so up1 f comma UPCF comma alpha minus LPCF comma alpha means here function is CF, so CF belongs to R of alpha, and likewise also CF belongs to R of alpha. We conclude that CF belongs to R alpha. So we have to prove in the prove in the form of integral means, so CF belongs to R of alpha means we know that minus a to b of t alpha equal to a to minus b of t alpha equal to a to b of t alpha. So since we know that upcf comma alpha equal to c into u upper bound of pf comma alpha, we are taking uh, for uh, for lower bound we take supremum, for upper bound we take infimum. So here upper bound we can take infimum take, if we take means a to, it will convert in the form of integral. So a to minus b cf d alpha, uh, cf d alpha equal to c into a to minus b f d alpha. So since we take lower bound means lp cf comma alpha equal to c l p f comma alpha means we can take a supremum means, how we write means this can be written minus a to b f d alpha equal to supremum of l p f comma alpha. So if we take supremum for l value means we can write, for lower bound we can put minus a to indicate that is a lower bound, so minus a to b f d alpha. So likewise also we are putting lower bound a to b cf d alpha equal to c into minus a to b f d alpha. Then then it can be converted into, if both the terms are equal means we can write in the form of a to b. So a to b cf d alpha equal to c into a to b f d alpha. We have a condition that is minus a to b f d alpha equal to a to upper bound f d alpha means we can write a to b f d alpha. So both conditions are equal means we can write this form. So likewise also we are writing this. Hope you all understand, and thank you.